didn't listen. So.
Oh, I just said, yeah, I'm just in the background. And
okay. Okay. So now Anne Churchland also joined the Slack. Okay. So probably we are now live on YouTube.
Yes. So we can slowly start, maybe. Still 2 minutes.
Yeah, we wait really until 3 o'clock, and then yeah. So we have already 47 attendees. Welcome everybody.
We are live on YouTube. Amira says thank you. Thank you for being there.
Right. Anybody? Do you have a watch with exactly? Okay. Yeah, I will.
But I mean,
yeah.
I think Valentin has.
Yes. Yeah. Okay. yeah. Yeah, cool. So I will start today's channel 2. So welcome everybody to ICMNS 2020. So this is channel 2 of this conference. And in this channel, we will first have a session on mean field methods from 15 to 17 o'clock. Then there will be a coffee break. And afterwards, there will be a second session on neural coding from 17:30 to 19:30. Okay, so shortly, let's be reminded that there is also a Slack channel for discussions, scientific discussions, for example. And then there's a chat option in the Zoom, and also a question and answer opportunity where you can ask questions. But now I will hand over to Eva Löcherbach, who shares the session and who co-organized the session. And yeah, so thank you, Eva, for all your help. And yeah, I will hand over to you.
Okay, thank you for all for being there, and welcome to the session on mean field methods. So we will start right ahead with the first talk, but before starting, just one comment. If you have questions concerning the talk, we would like you to use the question and answer button, which is downstairs in your Zoom window, okay? So don't use the chat, please use the question and answers button where you can ask your questions. You can also answer or comment to questions which are already there, and you can even upvote some of the existing questions to make them more popular if you would like to ask the same kind of question, for example, okay? We will try to keep an eye on these questions and answers button, okay. So we start with the first talk by Valentin Schmutz from EPFL in Lausanne. And we are very happy that he will be speaking about mean field limits for large networks of multidimensional spiking neurons. And we let you share your screen, Valentin, with us. And are happy to listen to your talk.
Thank you very much for the introduction. Can you hear me? Perfect. So at the microscopic scale, neural tissue is composed of individual neurons that can be connected to each other and that communicate through spikes. And so if we want to model a large network of neurons accurately, the resulting model is going to be very granular, which makes the mathematical analysis of this model challenging. One way to deal with this difficulty is to try to translate the original granular model into a fully continuous one, in hope that the continuous model will be easier to analyze and understand. To do this translation, most often one needs to take a limit And in this talk, we'll be only concerned by taking the limit n, the number of neurons, tends to infinity. In this spirit, an old question in theoretical neuroscience is whether we can approximate large networks of spiking neurons, so something very granular, by a population density equation, something completely continuous. And this population density equation are quite useful in computational neuroscience because with them you can study collective phenomena like synchronization, you can study information transmission, you can also use them to coarse-grain complex networks like a cortical column, and you can also derive what's called the next generation firing rate models directly from spiking neuron models. And this is elaborated in these two references. So this was all very high level. Now I'm going to walk you through like a very concrete example. So take a leaky integrated fire neuron. So here a neuron has a voltage variable that grows with time until it hits a threshold. When it hits a threshold, it emits a spike and the voltage is reset to a certain value, a fixed value that we choose here to be 0 for simplicity. So I think most of you are familiar with this model. So now we take the same model, but we take the same model, but with escape noise. And this means that we don't have a hard threshold anymore, like before, but instead, for each value, for each value V, each voltage value V, we have an instantaneous probability to emit a spike. That's called the intensity. And the intensity will be given as a function f of V. And we'll call the function f intensity function. So now the spike times are stochastic. And so a neuron can be seen as a stochastic process. We can now do an easy changer variable. So we go from voltage to age. And so now between spikes, we have this straight line because the age grows linearly with time. Sorry, I didn't explain what age was. So age is the time elapsed since last spike. And so we can go from voltage to age. And now in between spikes, we have these straight lines, but essentially it's exactly the same model as before. Sometimes it's useful to see neurons as particles because a neuron, like I said before, has a variable a, the age. So you can imagine a neuron as a point moving along this age axis. And so when there is no spike, the neuron moves to the right, and each time it emits a spike, it jumps to 0 instantaneously. And if you have many neurons, you can all draw them on this axis. And so if we have a network of n neurons, of course, we would like them to interact with each other. And so here we'll consider only the simplest form of interaction, which is mean field interaction, which means that all the neurons are connected to each other in a homogeneous way. So now the intensity function depends on A and X, and I will call X the mean field input. And the mean field input X will simply be the average over all the spike trains in the network convolved with the function H. And I call this function H the interaction function. So here I have described what could be called a mean field network of spike response model 0 neurons with escape noise. And in the mathematical literature, that would be called a mean field network of age-dependent Hawkes processes. So what happens when the number of neurons tends to infinity? So imagine that on its axis, you have more and more neurons. And I think we can kind of guess what's going to happen. And indeed, when n tends to infinity, you don't see the individual neurons anymore that are jumping around, but you just see a density rho. And this density rho evolves with time, and this evolution is given by a partial differential equation. So this is an example of population density equation. Just a bit of history on all this. So this n to infinity limit was conjectured some time ago by Wilson and Cohen and Gerstner. The equation you are seeing above is called the time-elapsed neuron network model of Pagdaman, Pertam, and Salor. And so these authors proved that this equation is well posed, and they did many analysis on this equation. And importantly, recently, Chevalier proved this n to infinity limit. So now it's rigorously proven. And for a similar proof on a slightly different model, but very much related, you can also look at these references. So in summary, if neurons have a memory of their spike history that is restricted to the time elapsed since last spike, that I call the age, then for mean field networks of spiking neurons, when the number of neurons tends to infinity, you get a population density equation. So now this result is very solid. It has been proven, and I think it's well accepted in the community. But the problem is that neurons, they have a memory of their recent spike history that goes beyond the last spike. And this is well known. So the recent spike history can have an impact on the spike times or the spike generation, and this is adaptation. And on top of this, if you see spikes as signals emitted from one neuron to another, the recent spike history can also modulate the effective amplitude of the spikes sent from one neuron to another. And this is short-term plasticity. So our goal in this project is to generalize this n to infinity result that I presented before for neurons with adaptation and short-term plasticity. So I'll first show you a motivating example with a short-term plasticity, and then I'll show you our general and rigorous result. So I'll take the same model I introduced, the exact same model I introduced in the introduction, and I'm going to add Zodix-Markram short-term plasticity. So a very well-known model of short-term plasticity. So now each neuron, like before, has an age variable A, but on top of this, it has two short-term plasticity variable, so a facilitation variable V and a depression variable Y. And so these variables are going to follow a system of stochastic differential equation. I write dz, the spike train of the neuron, and it's going to have intensity f of A and X. The age A follows the same dynamics that I explained in the introduction. And V and Y follow the Zodix-Markram model. So between spikes, V and Y relaxes towards a certain value. And at each spike time, V and Y jump according to a certain rule. Importantly, V and Y, variable V and Y are going to modulate the mean field input X. And so one way to get an approximation for the population density equation is to take the formula I showed you before. So the formula without short-term plasticity, and introduce a correction term here that I call R. And then using some heuristic, we can derive an evolution equation for this correction term R. And this is what we did in a recent paper with Gerstner and Schwager. And this equation, this population density equation, gives a very good numerical approximation of the real density equation. However, it is not exact. So even if numerically it's quite close, we know that it is not exact. And this kind of approximation results are quite common in theoretical neuroscience. And they are a bit frustrating from the mathematical point of view, because on the one hand, you can't prove that it is the n to infinity limit, because it's simply not the case. And on the other hand, it's very challenging to get a rigorous estimate of the error we're making. So bottom line, it's hard to prove anything with regards of this kind of approximation results. So then what is the exact population density equation? And we are going to answer this question and also prove this. So based on the model with short-term plasticity that I've shown you, I'm going to introduce now an abstract model, an abstract multidimensional model. So in the introduction, the neuron had only one variable, that was the age. And so a neuron was a particle moving in this one-dimensional space. And now I'm going to add an arbitrary number d of additional variables, m1, m2, blah, 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 until md. And now you have to see neurons as particles moving in this 1 plus d dimensional space. So we call this abstract model the age and leaky memory dependent Hawkes processes. So now each neuron has an age variable, like always, and it has leaky memory variables m. So m is a d-dimensional vector, and a and m are going to follow a system of stochastic differential equation. So dz, again, is the spectrum of the neuron, and it will have intensity f of a and m. And here the dependence on m is here to model adaptation. A follows the same dynamics as always, and m has a certain drift towards zero between spike. So between spike, it drifts towards zero at speed lambda. So lambda is a diagonal matrix with strictly positive terms. And when the neuron spikes, m will jump according to a certain jump rule gamma. Now, if we look at the mean field input, the interaction function h also depends on a and m, and this is for modeling short-term plasticity. So the motivation behind this abstract age and leaky memory dependent Hawkes process is that we want an abstract model on which we can map many interesting concrete models of spiking neurons. So for example, neurons with Zoldyck-Markram short-term plasticity, neurons with a moving threshold adaptation, the multi-timescale adaptive threshold models, and also the very general kernel-based models like the spike response model or the generalized linear model, if the refractory kernel is a finite sum of exponential kernels. So we want to prove that when n tends to infinity, if I write small gamma, the jump mapping, gamma m equal m plus capital gamma m, and b, the velocity field, then the population density equation for this age and leaky memory dependent Hawkes process is going to be this partial differential equation. So you see on the first line a continuity equation. On the second line is a border condition on the hyperplane a equals 0. On the third line is the equation for the mean field input. And on the fourth line is simply the initial condition. So I won't have time to explain this equation in more detail, but you can really understand it as a multidimensional generalization of the time-elapsed neural network model of Pagdaban, Pertam, and Salor. So the first step of the proof is to show propagation of chaos. And here we will use some well-established technique for Hawkes processes that were introduced by Delattre, Fournier, and Hoffman. And so we get a theorem saying that the empirical measure of our network is going to converge to the law of the limit process, ATMT. And you can understand the limit process ATMT as the process for one neuron in the n=infinity network. There's a bit of a heuristic way to understand it. And the important thing to get from this result is that if ALM is really the correct population density equation, then the law of this limit process should give a solution to this equation, should be a solution to this equation. So this leads to the second step. So we want to go from the law of the limit process to ALM, to the population density equation. So more specifically, writing rho t, the time marginals of the law of the limit process, we want to show that rho t solves ALM, the population density equation. We're going to proceed in two sub-steps. So first, we use the limit process ATMT to construct a path integral representation of rho t. And this nicely combines ideas presented in two papers from two slightly different disciplines, so No and Gerstner and Fournier-Lescherbach. And finally, with this representation, we'll be able to show that rho t is a solution to ALM. So just to give you an intuition of what I mean by path integral representation. So let's say that I'm interested to know what is the probability at time t to be in a certain state A hat M hat. So this is really just a cartoon. So I'm interested in this probability. And so I'm going to write this probability as the integral over all the possible trajectories a neuron can take from 0 to t, such that it arrives at time t in state A hat M hat, weighted by the probability of these trajectories. So this is really the intuition behind the path integral representation. And in our case, we can make all this fully rigorous. So now, armed with this representation, we can prove the final theorem, which says that if rho t denotes the time marginals of the law of the limit process, then rho t solves ALM. And first, we use the path integral representation to show that rho t has the right regularity. And so this is a little bit technical, but it is actually the point in the whole proof that has required the most work. And it's also maybe where we believe our proof might be a bit original. And then once we know that it has the right regularity, it's quite easy to show that rho t solves ALM. And this concludes our proof. So in conclusion, we have proved that for a large class of mean field networks of multidimensional spiking neurons, we get, when n tends to infinity, a multidimensional population density equation that we've called ALM. So in a sense, with this work, we have given a rigorous footing for this type of multidimensional population density equation. The details of the proof can be found in a preprint on arXiv. And naturally, the next step would be to analyze mathematically and numerically this equation to better understand the dynamics of large networks of spiking neurons. For this work, I have to warmly thank my supervisors. So Eva Lescherbach supervised all the mathematical part of this work. Thilo Schwalger and Wolfram Gerstner supervised the short-term plasticity project that I mentioned. And Wolfram Gerstner is also my PhD supervisor. At the beginning of this project, I had the chance to have many useful discussions with Monia Capana and Pablo Ferrari at the University of Buenos Aires. And more recently, I've been discussing some PDE aspects with Claudia Fonte and Stefan Michler. And also many thanks to the SAM team, the math department of UBA, and my lab, the LCN. And here are just the main mathematical references related to this work in case you are interested. Thank you very much for your attention.
Thank you very much, Valentin, for your beautiful talk. So now we have time for questions. I see that there are 2 questions, and so you might ask questions in the Q&A button. So there is a first question by Dimitri Todorov. The final equation looks quite complex in the general case. In which context do you hope to analytically study it, Valentin?
So that's a very good. That's a good question. I mean, so for a physicist, the final equation is a kind of master equation, and in a way, it's not. I think on certain aspects, it shouldn't be more difficult than the classical time-elapsed neural network model, so the refractory density equation. But there are some tricks that you can use with the refractory density equation, so the time-elapsed neural network model, that absolutely cannot be used with this generalization. So for me, I'm still not quite sure in what sense this equation is easy to analyze, but I think that we can do analytic work. It's certainly more difficult than the simpler case, but I'm not hopeless that we can do analytic work. But I don't know more about that because I haven't ventured in this direction yet.
Do you see the second question, Valentin? I will read it for everybody. It's by Daniel Scott.
Yes.
Could you please say, and I also wanted to ask this question, what the regularity condition that you were evoking is actually about, this regularity on?
Yes, okay. So maybe I will try to go back to the slide. Let me see, how can I do that? Perfect. So, no, sorry. Am I sharing my screen now, right? So I said, has the right regularity. Yes, well, so at the end of the first part of the proof, we have this object. So the law of a limit process. And so I wanted to be in a L1 setup. So meaning that the initial condition has a density, and I wanted that at each time, the time marginal has a density. And so the first thing that I had to show was that at each time, indeed, you have a nice density and you don't have atoms in rho. So rho is really a density with respect to the Lebesgue measure. And you could get this result with the path integral representation. And on top of that, with the path integral representation, you could get that rho t is in CL1. Unfortunately, I don't have a slide for this, but I hope this is clear enough.
Thank you. Thank you, Valentin. So if there are other participants who want to ask questions, Thilo told me that you can also wave hands. I don't know if you're able to, and it's complicated, more complicated Zoom than video conferences.
So there should be some possibility to raise a hand if you want to ask a question live.
We can
we
even give you
could
the
do this.
possibility to speak. Yeah.
Otherwise, maybe I ask in the meantime another question to Valentin. So you showed a result that is valid for n to infinity. Is there some hope that you can get some results about fluctuations for finite n?
Yes, so I don't know, I'm not at all an expert on this, but I'll see two strategies. So one is to use a bit the strategy that was used in a recent paper by Julien Chevalier, which is to, instead of showing that, oh yes, it converges to the law of the limit process, to instead of getting this kind of result, to get central limit theorem kind of result. So where you have a little bit of fluctuation and you see that, when n is large, you have the right fluctuation in a sense. And so that would be one route. And so to see if we could generalize this result of Julien Chevalier. And the other way would be to have a more heuristic approach and to try if one could use the approach you used in the 2017 paper on this kind of multidimensional equation. So then that would be not something very provable, but we could test that if your approach can be applied in a multidimensional population, for a multidimensional population density equation. And I don't know if it is possible, but I'm really interested to think about it.
Thank you. This is the perfect transition to the next talk, actually. So, because you have already quoted, Valentin, the paper by Julien, who is also in the audience. At least I think I saw him somewhere. So this is a good transition to the next talk. So thank you again, Valentin, for your beautiful first talk. And the next talk is given by Guilherme Ost, who will show up soon, I hope. So Guilherme Ost is now assistant professor at the Federal University in Rio de Janeiro. And he will share his screen and to give a talk on a joint work with Julien Chevalier on spatially extended Hawkes processes and their connections with neural field equations. And there will be also results about fluctuations in them. So Guilherme, you have 25 minutes and we will be listening to you. For the moment, we just see the beautiful landscape. Perfect.
Does it work? Hello, Eva?
Everything is fine. I hear you. I see your slides. So
perfect.
If you want, you can start your talk.
Okay. So Eva, thank you very much for the invitation, for the introduction. Before starting, I also would like to thank all the people involved in the organization of this very nice conference on mathematical neuroscience, especially in these days. And as I can see here from the title of my presentation, I'll be talking about Hawkes processes and their connection with neural field equations. So all the results presented here are based on two papers recently published in the SPA journal. So they are product of joint works with Aline Duarte from São Paulo, Eva Lecherbat from Paris, and Julien Chevalier from Grenoble. Okay. And what are the main contributions of our work? So the first one, from the first paper, I would say that we established rigorously a relationship between mean field limits of spatially structured Hawkes processes with neural field equations. And in the second paper, I would say that our main contribution is to complement the results from the first paper by studying the fluctuations of spatially structured Hawkes processes and connecting it with the stochastic neural field equations. So why are these results interesting? So as Valentin mentioned, imagine that you wanna understand properties of a very large networks, and then one way of doing this is through simulations. But then depending on how large is your network and how complex is your model that you want to implement in your algorithm, this can be very high computational demanding. So an alternative way is then to try to simplify the model, to try to derive simplified descriptions of the model. And this is where the mean field limit theory comes in. So, and even with these simplified descriptions, you can provide useful insights of how the activity of the network is related to the underlying neural circuitry. Okay, and as some of you might know, although this theory of mean field limits is very nice, there is a huge or a big downside, which is at the limit, when you derive your macroscopic equation describing how would your network evolve when it's very large, they treat the neurons as if they were independent. And then if you look at real data, you'll see even if your network is very large, you'll see that you might have neurons which are still correlated. And this is known in the literature as the finite size effects, in a way to try to account for this finite size effects is try to study the fluctuations. And that's why fluctuations are very important, okay? So in the rest of my talk, I will try to define precisely the Hawkes model we use, and then relate the results of mean field limits with neural field equations, and then I will go through fluctuations of this stochastic model. Okay, so Hawkes processes, they are just point processes on R, let's say R plus. They were introduced by Hawkes in the 70s. And very recently, it became a very popular model in many areas, including finance and neuroscience. And then just to quote to cite some literature involving neural modeling via Hawkes processes, I'd like to stress the paper from Patricia Renaud-Boré and collaborators, where they developed lasso methods. And then there is a paper from Shia Brown and collaborators where they derive some concentration inequalities for second-order statistics. And then the paper from Suzanne de Plives and Evelyn Chebra, where they have this mean field description exhibiting oscillatory behavior. And then there are papers from Julien Chevalier, where he derives some mean field descriptions and also studied the fluctuations of age-structured Hawkes process, as Valentin just mentioned in his talk. And more recently, there is a paper from Antonio Galvis, Enrico Presucci, Evelyn Chebra, and Christophe Pouzat, where they also derive a mean field description modeling short-term memory. Okay, so let me introduce a notation and give you the precise definition of Hawkes, at least the example of Hawkes process that we consider. So I have a network with n neurons. For each neuron, we have an associated spike train. So I will denote this by capital Ni. So the marks in red here would represent the spikes of neuron I. So this spike train induces a point measure, which gives masses, which is concentrated on the spike trains of I. And usually people describe how they describe the evolution of the process in terms of an intensity process. So lambda I of t here would represent, so this is called the intensity of neuron I. And then lambda I of t would represent the probability to have a spike of observing a spike of I at time t. And the important thing here is that this quantity here is random. It depends on the past history of spikes. And in this talk, I'll be focused on a specific sample. So lambda I here for me is f of UIT. So U here is the membrane potential at time t. And there is, and so we assume here that the UIT, it changes through time due to spikes as follows. So there is this term here indicating that there is a decay, an exponential decay with rate alpha. Okay, each neuron is being attracted to zero in this sense. And then there is the second term here where we introduce the dependence of the model. So essentially here, it's saying that for whenever a neuron J spikes, it gives a quantity W of xj, xi. So xj here will be the position of the neuron J. I am assuming that for simplicity, this is xj will be j over n. So this is everything in the units unit interval. And then at the end, what neuron I is feeling is an average effect of all those weighted spikes. Okay, and U0 here will represent the initial condition. So just some terminology, people call this F a firing rate, could be a logistic function, for instance. The W here is called, or would model the synaptic couplings. Will be a nice example is the Mexican head function. Here is just this U0 here will correspond to the initial condition of our process, and the alpha here will be the leakage rate. Okay. And just for the remaining part of my talk, I will denote Ni of t, the number of spikes of neuron I on the interval 0t. Okay. So let's discuss very briefly the results we might have, we might able to prove and relate this with neural field equations. So the question of interest here is to understand the convergence of this point process as the size of network gets larger and larger. Okay, so there is I would say a sort of law of large numbers in the following sense. So this will be our preliminary result. So if I take the sum over Ni of t, so and divide by n, so this will be the an average of observed spiking in my network up to time t, and then we can show that this in fact converges to a given number, and then moreover we can identify this number as an integral over x here would be the positions. Okay, remember that the positions are all contained in the interval 0, 1. And for each x, I integrated from time 0 to t a function like lambda t of x. So we identify this number and we represent it as this. And then it turns out from our analysis that this lambda t of x can be written as a function of utx. Okay, and this utx solves a scalar neural field equation. Okay. So in a nutshell, this equation is just describing the macroscopic behavior of the point process that I just defined. So you see here, there is this minus alpha ut, it's this exponential decay. And then there is this non-linear term here is telling me that continuously the neuron is being receiving spikes from the others. So this would represent the fraction of neurons spiking at time t at position y, and then whenever it spikes, it gives you w of y to x, and then I'm integrating this over all possible positions. Okay, and of course, in this sense, UIT can be understood as the mean representation at time t of a typical neuron located in position x, embedded in an infinite network of neurons. And so this type of equations has been introduced by Amari, Wilson, and Cohen in the 70s. Okay, so this is a first description of a network at the limit, and then we can be much more precise. So for each x, if I denote n bar of x as a Poisson process with intensity lambda tx, okay, and I denote the n bar t as the number of points of these processes on 0t, we can also show that if I compare the number of points of my Hawkes processes at each possible time, and for each neuron, we can show that this goes to 0 as square root 1 of square root of n. Okay, so in some sense, we are approximating our Hawkes processes by a family of Poisson, non-homogeneous Poisson point processes with this lambda, with this intensity lambda t of x. Okay, and from this type of result, we can also show that if I look to for each neuron, I compare the evolution of the main problem potential of neuron I with the neural field equation. If you look the L1 distance for each neuron, this also goes to 0 as n goes to infinity. Okay, and here the expectation is taken with respect to the randomness present in the jumps. Okay, so this is somehow a much better description than just the law of large numbers that we saw before. Okay, so in some sense, I'm saying that the UT here, the solution of the mean field, the neural field equation, could be an approximation for the finite size system U1T, UNT. Okay, and as I mentioned in the very beginning of my talk, by doing this mean field approximation, and then you treat the neurons at the limit as if they were independent. So meaning that if you take the correlation, if you want to study the correlation of two pairs here of neurons, and then you study the correlation as a function of n, and then you see that at the limit this will be 0. Okay, and then a natural question at this point is, can you provide a finer approximation? Okay, and that's why we study fluctuations. So let me introduce some notation. So I will call you see, I compare the UT minus the solution of the neural field equation, and then I'm scaling this by square root of n. So I'm amplifying this difference, and I call this eta n of xi. And my idea here is to try to give an heuristic argument to derive an equation that this eta should satisfies when n it's very large. Okay. So recall that at 0, these two guys are equal. So eta at 0 will be 0. Okay. So I just recall you the evolution for the Hawkes process for the UIT is this, and the evolution equation for the neural field equation. Okay. So let me just do the first approximation is just to change the integral as a sum like this. Okay, it's just Riemann approximation. And then if I sum, so if I compare with eta, I take the derivative with respect to t here, and you see there is this minus alpha in both sides. So this gives me back again the eta, and then I have this sum here 1 over n. W and square, and then I have the j here, and then I have f of u t xj here. Okay. So if I add and subtract this term here, okay, I get immediately this equation. So I just rewrote it. Okay. And now I split it into parts. So this nj and fuj here, and f big U with f small u. Okay, and then if I apply Taylor expansion here, you see that this term can be written as the derivative times the difference. Since I multiply by square root of n, I recover the eta n of t at the position xj. Okay, and then so this is just explained. And then since I will rewrote this as an integral equation, and just want to introduce some notations. So I will call, so if I integrate this term from 0 to t, will be clear in a minute why I'm doing this. And then I multiply this by e of alpha s here in this big parenthesis, this expression, integrate over ds, and I call this m and t of xi, because this depends, at the end, depends on xi. So if you do this, I replace this approximation here, you get the eta. So I'm integrating here, right? Should be this integral from 0 to t e minus alpha t minus s, because I have this exponential loss. So here you recognize exactly this term when I replace this difference by f prime. And since I should have this e to the minus ts, and in my definition I have only s here, I also get this extra term. Okay. And what important here is this term here. That's why I wrote in this purposely in this way. This term here is a martingale. You can check. Okay. And then from this, it should be, if you believe that this converges to some object, and then I can apply sort of central martingale central limit theorem. And then I obtain, as n goes to infinity, an equation like this. So gamma t would represent the limit of the eta. And then you can recognize that I just replaced the previous equation, the previous sum, by an integral over all the positions. And here I have the e minus alpha t times this term here, which would call a Gaussian term, okay, which comes from this martingale central limit theorem. Okay, so this term here is a Gaussian with mean 0, and they are correlated, so you can check that this is the correlation, and you see that the function w plays an important role here. Okay, and then since this is a Gaussian, there is correlated. You can rewrite after some work this term here as an integral with respect to of this sort, with respect to a Gaussian random field, and to make sense of this equation of this object, and then to make sense of this equation, we use this Walsh theory of stochastic integration. Okay. I won't have time to discuss details, but we can do it later if you want. So in conclusion, from the heuristics, I hope it's clear that asymptotically, the vector of these etas, so the vector of my fluctuations, can be described as a solution of the SPD of the following form. So I'm writing not in the integral form, but in the differential form. So and then you would get this equation, okay, where this is a stochastic term, okay. And this big W here is a Gaussian random field. So, so in the last 4 minutes that I have, I just would like to show you some consequence of this result. So the solution of the neural field equation, as I just said, so this is the conclusion up to this point, can be thought as an approximation, 0th order approximation of our finite system. And then if I define my process y and t as the u plus 1 over square root of n gamma t, so gamma will be the solution of the previous equation, this can be seen as so this is a finer approximation, and we could call this as a first order approximation of finite system, just a name, okay? And then if you look at the equation that this y process satisfies, it's not difficult to check. So if you remember the equation that the small u satisfies, it's minus alpha u, then the integral with respect to positions w f u, and then the other terms are the terms coming from the SPD gamma, okay? And then if you think about it, this guy here, this term here can be well approximated by f of y and ty, okay, by definition. And this guy u here, it's also well approximated by this, I can replace it by this yn of t. And when you do this replacement, so I'm just say it again here. So when you do these replacements, the equation that you get is a stochastic version of the original narrow field equation. So it can be written like this. So we forgot about this stochastic term. This would be exactly the stochastic narrow field equation coming from the mean field limits. And then by studying the fluctuations, we can derive a stochastic version of this narrow field equation. And it's a very nice result that we got is, first, we can make sense of this equation by using the Walsh theory. And by the way, there is a paper from Olivier Forgeras where it explains very nice how this theory could be applied. The Walsh theory could be applied for make sense of those type of neural field equations, stochastic neural field equations. And as our final result, so under some assumptions like F, U, and W are smooth, okay, and the derivative of F and the second derivative of F are bounded, we can show that if we compare the solution of this phi with the narrow field equation, so this is the square root of the L2 norm of this is 1 over n, the case with 1 over n, and then the V and the Y, they also their distance is, the error is 1 over n essentially. Okay, so I hope that's clear enough, and that's it that I want to share with you. Thank you.
Thank you very much, Guilherme, for this talk. Oh, I have to look at the questions. Is it possible to learn W rather than fixing it? For example, assuming.
That's a good question. So I keep I'm keeping asking myself this question also to other people. I do believe that it should be possible in some sense, because once we have this equation here, we can try to do what we do in statistics, which is called the confidence interval somehow. I'm being very imprecise here, but I would say for the moment it's not so clear how to do this, but I would say that once we develop a well theory to study the properties of this equation and etc., we can try to do what people call in statistics a confidence interval, and from this maybe we could infer this W. Okay, I don't know if that answers the question, but that's what I have.
So there are two related questions then, I would say, by Lucas Wessels and James McLaurin. So what is the distribution of the Gaussian random field? Is it space-time white noise? And same kind of question by James.
Oops. So this is Gaussian random field. If I go back here, maybe here. It's you see, this is just this when we wrote this as an integral with respect to Gaussian random field, is just to say that this would represent the Gaussian stochastic term here, which is our Gaussian process. Okay, so I should say, so this is a Gaussian, so we can have some regularity properties of the solutions by exploring this Walsh theory. Okay, and then if you look at least in the Forgeras paper, I guess what I'm calling Gaussian random field and what he calls there is exactly the white noise process. Okay, and then I don't know. Does this answer the question, or?
I guess.
Okay.
Yeah. Yeah. Julien is confirming.
Yeah. Thanks, Julien. And of course, I should say that, so this is just an heuristics. The rigorous result, we had to define this through measure measure valid processes and etc. So it's a bit more complicated, but all the details you can find on the joint paper with Julien. Okay.
Yeah. So we have been working, Guilherme, about same kinds of processes, but with reset at each spiking time. Yes. Would it be easy to extend your work to the framework of, of neurons that go back to zero once they spiked?
Yeah. So I have been discussing with Julien questions like what should we do next, and he can confirm this. And I was asking him to that I think my impression is that it will be possible to join, to unify the 2 point of views in the sense that I could consider a model, I guess. I could consider a model with the spatial structure and also a model where we keep track of the last spiking time, the age, what's called the age, right? I guess it should be possible to derive mean field descriptions of models with this type of with these ingredients, and also it should be possible to derive an SPDs to explain how this the process to explain the fluctuations of the process with respect to its mean field limit.
Are there any other questions from the audience? Do you see any waved hands, Thilo? No. I don't see no, okay. You were speaking about, one last second, because we have to switch to the next talk, but you were speaking about simulations. Did you do some? I know that.
Yeah, so this you can ask for, I'm sure that Julien has implemented some simulations of because you can simulate this neural field equation and compare it with the simulations coming from the point process here. Okay. Mm-hmm. Unfortunately, I don't have the pictures here, so this is for sure it can be done. It's already done, but for the moment we don't have simulations to see how, to better see these fluctuations and how yeah, so we don't have simulations to better see the behavior of this the fluctuation of the solutions of this gamma t.
Okay. Thank you very much, Guilherme, for your talk.
Okay. So thank you.
I guess it's
so
time. So it's time to switch to the next talk. So we leave the stochastic world for a bit, but Delphine Salor has already been quoted in the first talk by Valentin. So the next talk will be given by Delphine Salor from Sorbonne Université, and she will speak about qualitative analysis on a PDE model of your network. And we are happy to have you there, but your microphone is not yet switched on. So yeah, now it's perfect.
Okay. Up and hop. Alors je partage.
Je crois que tu devais d'abord. Ah non, ça allait.
Do you see the slides?
No, I just see some white window. I guess you have to stop.
Okay, if I put this. C'est marqué votre partage d'écran est en pause. Ah, ok. Bah oui, yes, but.
I think you have to open the file before sharing your screen. So maybe you stop sharing your screen, you go back one step.
Okay.
Open your file and then you share. Yeah.
Okay. Up. Up.
Yeah, perfect.
Okay. You see, it's okay?
Yeah.
Okay, nice. Okay, so I thank the organizer for this invitation. And
we don't see, excuse me, we don't see the full screen. So
okay.
maybe you can.
You don't see, because I don't see what you see.
Now
Yeah,
it's
of course.
now it's great.
perfect.
Okay. Okay, so I talk of a qualitative analysis on a PDU model of neural networks. So it's a joint work with Maria Cáceres and Ricarda Schneider from sorry.
Canada, Maria at least.
In Spain, sorry, I just it's a psychological. José Antonio Carrillo from Imperial College of London, Kota Ikeda from Japan, and Benoît Pertam and Didier Smets from Sorbonne University. So here the general problematic that we have studied is to understand how collective neural dynamics can emerge from individual neurons. And in particular, we were interested of the emergence of periodic solution. That is, when can we have observe the synchronization of neurons? And we will try to answer this question with respect different aspects that I will tell us after. And so in general, the aspects depend on the intrinsic dynamic of each neuron, the type of coupling, memory effects, delay of transmission. So in our study, we have chosen to describe the neuron via its action potential. So I think that everybody knows this picture, but I just show it to recall. So here we see the membrane voltage of the neurons, and if the membrane voltage reach a value that we call the action potential, then there is a spike, and the neuron discharge and can communicate with the other neurons. So our model is the following. So it's a model inspired from the integrate and fire model. And here, the neuron is described via its membrane potential. So V is assumed to be to live in -infinity VF, where VF is the action potential. So this means that when the neuron reaches the value VF, the neuron discharge. And we also assume that when the neuron potential reaches the value VF, instantaneously the membrane potential reset to the value VR. Okay, so with this, so there's several models proposed via this kind of modelization, where the neuron is modeled by a Leakey integrate and fire model, and we have studied the model proposed by Brunel and Hakim, which is the following one. So there are several notations that I will explain. So the part here is due to the Leakey integrate and fire dynamic assumed on the neurons. Here it is a noise, and here it is the neurons that have discharged and come back to the value VR. Okay, and N of t is here the flux of neurons with discharge. So how we compute this N of t? N of t is equal to minus the derivative of p at VF t. Okay, so this means that in particular we have the mass conservation with this. And with this flux of neurons, we can compute that we call the amplitude of stimulation that receives the neuron, or the neuron at time t, and this amplitude of stimulation we call it x of t. And here we can observe that we have a parameter b, and this parameter b model essentially the strength of interconnection of the neurons. And this parameter have a sign. If b is strictly positive, we are in excitatory networks, and when b is negative, we are in inhibitory case. Okay, and if b equals 0, the equation is linear, and we have no interconnection between the neurons. So after I will show you a draw of the solution to see intuitively what happens. And now what we have chosen for x of t, there are several choices, but we have made two choices. The first one is the most natural, essentially x of t equal n of t. So this means that we assume that the amplitude of stimulation of the neurons is exactly equal to the flux of neurons with discharge. And so we will see that here the dynamic is very singular. So the second case that we have considered is the case where x of t is equal n of t minus d, where d is strictly positive. That is that we assume that we have a delay, on the equation. So the neurons must wait some time to receive the signal of the other neurons. So I will first begin to consider this case to understand what happens, and after I will consider the last case with delay, where we can see more complex patterns. So if we consider the case where x of t is equal to n of t, so this equation has been studied by many authors that I mentioned here. What happens? The problem is that the total activity of the networks acts instantaneously on the networks. And in particular, this will mean that if you are in the excitatory case, so that is b strictly bigger than 0, then you will have blow up. So whatever the excitatory case, even if b is very small, you have blow up, but not always. You have blow up if you choose well the solution. Okay, the initial data, not the solution. And if b is large enough, you have always blow up. However, as soon b is negative, so this means when you are in the inhibitory case, you can prove that you have global solution in the solution is well defined. So more precisely, when you make numerical simulation, in the excitatory case, at least, you have you can see two types of dynamic. So it's not very complex. Either the solution converges to a stationary state, so it is the case here. So here it's the initial data. So the flux of neurons is computed is equal to minus the derivative at this point here. And you see here that the dynamic, you have convergence to a stationary state. The other case is the case here, where here you see that you have an initial data which is like that, and the solution, so here VF here is equal to 2, VR you see here is equal to 1 in these simulations, and you see that you have blow up. So what does this mean? This means that n of t, the flux of neurons with this size, get bigger and bigger and goes to plus infinity at finite time. Okay. So when you see this, what can you say? You say, okay, with this equation, I cannot observe many patterns, because either we have convergence to stationary states for excitatory case with B small enough and a well-chosen initial data, either we have blow up. So, we want to eventually observe periodic solutions. Alors, so there is one way eventually to eventually observe a periodic solution with this kind of solution of equation, is to try to define the solution after the blow up. So there are some authors that try to do this. So that's up here. So it's the work of Delarue, Inglis, Ribbenthaler, and Torre. but so it is probably work of with probability, and I don't think that they obtain now the existence of periodic solution, but here only no, I'm sure that it is not, in fact. And so here I just concentrate on deterministic tools. So so what we have done, so okay, you cannot have theory on periodic solution, but at least we can study the stationary state and eventually the convergence to the stationary state. Okay, so the study of the stationary state, okay, we have an explicit solution here. With the mass conservation, we see that we have an implicit condition on the n infinity, the n infinity. And what we observe that in the inhibitory case, or if the excitatory case is small enough, B is small enough, we have a unique stationary state. For intermediate B, we can have at least 2 stationary states. And if B is large enough, there is no stationary states. And it is normal because if B is large enough, we have always blow up. And if we have always blow up, we cannot have stationary state. It's obvious. Okay. And okay, so with no interconnection, we have even better. With entropy type inequality, we can prove that the solution converge exponentially fast to its stationary state. So it's a work of Caceres, Carrillo, and Pertam. So what we have done with Carrillo, Pertam, and Didier Smets is to consider the case, the nonlinear case, because here B equals 0, it's linear. And what did we prove theoretically? So I don't, here I don't put the proof, but I just give the results because the proof is quite technical. So in the inhibitory case, we have obtained a uniform estimate on the flux of the neuron independently of B. So it is important and of the initial data. It is important because when B is very large, even if B is negative, the nonlinearity is very strong. So this means it is difficult to tackle. Okay, so, but however, here we have arrived to prove uniform estimate on the flux of the neuron. So it is the first step to obtain eventually the fact that the stationary state is a global attractor. And it is the second point of our proof. So via essentially entropy method, okay, but I don't give the details, but we have proved that effectively we have a global attractor if B is small enough. So the fact that B is small enough is due to the fact that we can use here the entropy method only if B is not too large. Even if numerically we think that for all B negative, it is a global attractor. In the excitatory case, we have also estimates on N, but of course it depends on the initial data and on B, because if B is large enough or if the initial data is too close to VF, is too concentrated around VF, we have blow up. And we have shown the same kind of result, except that here we have not a global attractor due to the blow up, but we have a convergence to a unique stationary state for sufficiently weak interconnection if we well choose the initial data. So if the initial data is not too much concentrated near VF. Okay, so it is the case with without delay. So we say now what happens if we add delay? Maybe that with this we can have periodic solution. So now the n in here, instead of having n of t, I put n of t minus d, where d is strictly positive. And what we have proved with Caceres rule and Ricardo Schneider is that, of course, we lose instantaneously dynamics, so we have no more blow up. And we can even prove that we have existence and uniqueness of a global classical solution. And okay, and we also have exponential convergence to unique stationary state as soon B is small enough. So that means that we are not too, we are close to a linear equation because B is quite small. Okay. So here I just give the idea of the proof of the global existence. So the first point is to make a change of variable to obtain a Stefan type equation and to obtain an explicit equation on the flux n. This allowing us with a fixed point argument to obtain a local existence. And after, to control the solution, we construct a super solution or an upper solution to obtain uniform estimate, a priori estimate on the flux n, and this will and we will be able to conclude to a global existence. Now, okay, now if we say, if I ask, can we have now, okay, the solution is well posed, can we have a periodic solution on this equation? I don't know what you think intuitively, but if we assume that B is large enough, you remember that when we didn't have a delay, the solution always blow up, and in particular, we didn't have stationary states. So, and the second observation is that the stationary states of this equation with delay are the same as the stationary state without delay. Okay, because the stationary state are the independent of t. So this means that, okay, so this means that for large enough, B large enough, we know that we do not have a stationary state, and we also know that the solution is globally defined. So this means that at least we know that the solution will not converge to stationary state. So does this mean that we'll have periodic solutions? But in fact, okay, maybe naively we can say, okay, it's right, we have periodic solution. But in fact, it's not true. Because periodic solution, intuitively, we think that the periodic solution oscillates around stationary states. So here we don't have stationary state. So what happened in this situation for the excitatory case when B is large enough is that, in fact, we have some kind, so I made some simulation here. We have no periodic solution, but the n of t, so here it's a variable t, here it's n of t. N of t goes to plus infinity when t goes to plus infinity. Okay, so we have explosion of the flux of neuron which discharge, but okay, we do not have blow up. So we can nevertheless, we can observe some. It's not periodic, but you can observe some patterns which repeat but get larger and larger, and the length here seems to be the same. So they, okay, it's like you have some synchronization which get higher and higher. Okay, so unfortunately, even if we add delay in the excitatory case, we do not observe periodic solution. So this does not mean that the periodic solution does not exist. Huh? This only means that here, with numerical simulation, we didn't observe it. But I think that there is no periodic solution. Huh? Okay, so okay, it's in the excitatory case, we do not have periodic solution. But what happened in the inhibitory case? So in the inhibitory case, without delay, numerically, we observe no periodic solution, and we even observe that the solution goes very fast to its stationary state. Now, if we put a delay, we will observe interesting patterns. So I make, so I just put the equation that we observe. So here we assume that B is small, negative, and B very, very small, or the absolute value very, very large. Huh? Here I put D equal 1 and VF equals 0 to do not have too much notations. So we have made some numerical simulation that I hope that Attends, I just put the numerical simulation. OK. Hop. Partager l'écran. OK. Faire comme ça. Voilà. OK. And voilà. What do you observe? It's funny, huh? You observe some kind of Gaussian. We go from the left to the right. Okay. So the dynamic seems very simple in some sense. We say, okay, it's like a Gaussian. So here the solution, huh? Okay. It's like a Gaussian. And when we have observed it numerically, we say, okay, maybe we can say something theoretically. So it's a current work. Hein? So, je vais juste faire partager l'écran. So it's a current work. So I just give the idea that we want to do. Up. Okay, so we have seen numerically, we say, okay, maybe we can make some description theoretically. So what we have done, we have assumed that B is very, very small. So that means that we want to make an asymptotic analysis when we are in a very, very inhibitory case. And we have searched here the solution, the solution of the form P of TV is equal to a function phi of V minus C of T, so like a wave which propagates from the left to the right, plus a remainder term, where the remainder term have to be very small. And we have proved that, in fact, we can have the control of the remainder term with respect to the flux of neurons with discharge. And numerically, and we know that when B is very large, N gets very small. So we think that this kind of approximation is good when B goes to minus infinity. And we have searched the equation of C of T. We want that C of T is equal to C prime of T plus C of T is equal to B N of T minus 1. But heuristically, N of T minus 1 is minus dVP at VF. So it is minus dV of this quantity. Okay, and we put the remainder term equal to 0. So this means that asymptotically, we find that the speed of the propagation from the left to the right satisfied this delay equation. So now the question is, does we have periodic solution of this delay equation? Because if we have periodic solution on this delay equation, and if the solution can be approximated by this quantity, whereas phi here is a Gaussian, then it's okay. We have theoretically prove the fact that the solution effectively have the dynamic of that we have observed numerically. And so what we have proved is that if B is small enough, then there exists non-trivial periodic solution of this equation. So the idea of the proof is inspired from Adler and Tomyuk. So it's essentially a study of the eigenvalues of the linear problem of this equation with a good control. Oui?
Tu as 2 minutes.
I finished. Huh? I just finished. It's the end of my talk. And an application of the fixed point. Okay, so we have made numerical simulation, in fact, to compare. Alors here it's the moment of the real solution of our equation. And here is the solution of the delay equation. Alors, so the problem is that here you see that it does not fit exactly, but the problem is that here we have chosen B equal minus 50. And when we study the problem, so I don't give the details here, we see that the judicious parameter is ln of B, of minus B. And ln of B goes very, very, very slowly to minus infinity. and it is very difficult to make simulation when B is very large, because the simulation are not accurate anymore. So okay, so we cannot numerically check our formally approximation, but at least for B equal minus 50, we see that it begin to looks like to be quite depends of the interpretation, but I am quite happy of what happened here. So I thank you very much, and I finish my talk.
Thank you very much, Delphine, for your beautiful talk. Are there any questions? Oh.
No, it's okay.
So there's a question from Nathalie Schieferstein. It seemed the periodic solution in your numerical simulation was a Gaussian traveling back and forth.
Mm-hmm.
If so, why? So why the Gaussian character?
Why the Gaussian? I come back to here. In fact, okay, I don't know exactly. I don't know explain it intuitively, but I come back to the slides.
There's a extension to this question. So why is it a Gaussian with a finite, or with the constant width?
Sorry, yes, I was.
Okay, so here, in fact, we have we have found the Gaussian only with by making compute. In fact, we okay, I don't put all the computation here. In fact, I make one solution of this equation with here. I put it equal to 0, because n of t, when b is very small, n of t is quite equal to 0. Okay, and I inject this phi here, and we find that it is a Gaussian type, that phi must check a Gaussian equation. And after we compute the remainder term with respect to the Gaussian equation. In fact, we have inputted the Gaussian equation. So why exactly this is the case? It is because this kind of equation, we obtain some, if we put a 0 here, the solution of this kind of type of equation is of Gaussian type.
Did you see the question? So Natalie is insisting about why the width is constant, and Etienne Tenré is also asking why, because we have a compact support. I mean, the V value is always bounded.
Okay. No. Okay, because in fact, yes, because what happened is we have compact support, yes, but when B is very negative, in fact, I put the equation on, you can put this equation on R by extending P equals 0 on VF plus infinity. Okay, but when B is very small, in fact, on the solution defined on R is not equal to 0 on VF plus infinity, but is very small. The Gaussian is very small, because the Gaussian is very from the left. So it's coherent that it is a good that it can be a good approximation, because the Gaussian goes very fast, in fact, from the left, and n of t is very small. So when you compare our approximation with a Gaussian, which is defined on R, and the solution that we can project on R only by putting zero on VF plus infinity, you can see that. But we don't have proof. Okay, we can see intuitively that it may be true. I don't know if if it is clear. No.
Yes.
Yes.
Can I ask a short question?
Yeah.
Can you clarify? Yeah, we are short on time, but can you shortly clarify what is the main difference to the classical work by Brunel and Hakim that you cited, where also the emergence of oscillation in this model with delay was analyzed.
Sorry, can you repeat the question, because sorry, I didn't heard.
Can you hear me?
Yes, it's okay. Can you repeat the question, because
yes. So what is the main difference to the work by Brunel and Hakim that you mentioned, where they also studied the emergence of oscillations in the presence of delays and studied the Hopf bifurcation and made a weakly nonlinear analysis of this via the Hopf normal form and so on.
Yes. No. In fact, yes. They also, they also study, in fact, numerically and make a bifurcation analysis on the case with delay. But I think that, in fact, our study, so it's a work in. The work is not finished. In fact, here what we have considered is the case very, very inhibitory, and in fact, the aim is to describe precisely the shape of the solution when B is very, very small. And I don't think that, in my knowledge, I don't think that Brunel and Hakim, they prove periodic solution. No, they show numerically periodic solution and some bifurcation analysis, but I don't think that they put it like a Gaussian with a remainder term. And also, I did not mention here, but that we have done also, we have make here a profile of the solution of this equation when B goes to -infinity of the periodic solution, because the theorem here give you existence of periodic solution, but you don't know the shape of the periodic solution. And here we have made some work that I do not mention here, but we have made a current work where we try to describe the profile of the solution when B goes to -infinity.
Okay, thank you for your question, for your answer.
Yeah, so I think we have to stop. I'm sorry, Etienne, there was another question by Etienne, but I propose you to discuss about this entre vous.
Okay.
English. So thank you again, Delphine, for your beautiful talk. And now we are heading to the last talk of this session, which is given by Ernest Montbrió from University Pompeu Fabra in Barcelona. So we are waiting for him to, he has already appeared, we're waiting for his slides. So he will speak about the influence of spike resetting on the collective dynamics of quadratic interval fire neurons. And so looking forward to listening to your talk, Ernest.
Thank you very much, Eva. Can you hear my slides?
We see your slides. We hear you very well.
Okay, so thank you, Eva and Thilo, for inviting me to give this talk, and also thank you to Daniele Abitabile for organizing the conference and for all the time he has invested in that. Okay, I want to talk about the collective dynamics of networks of QIF neurons, of quadratic interval neurons, and in particular, I would like to focus on the influence of the spike resetting on the collective dynamics of these networks. And I'm in this session about neural field models of neural mass models or mean field theory, and I will use a mean field model to investigate that. Excuse me.
It was perfect before, you know.
Yeah. But sorry. Okay. Let me start with the quadratic intercamp-fire model. This is the definition of this model. It's a first order or differential equation, which describes the evolution of the membrane potential of a neuron. This eta represents some external current that is receiving this neuron, and here I represented, and this function is parabolic. So you see here the parabola. When this eta is a negative, this function here has two zeros. One of them is this stable fixed point, and the other one is this unstable fixed point. This represents the resting state of the cell, and this represents the excitability threshold of the cell. In this figure, here you see the time course of a simulation in which this cell receives now an extra input, okay, this periodic input, and it shows that the neuron can integrate inputs, and when the voltage reaches this threshold value, the neuron produces a spike, and then the membrane voltage diverges, and it has to be reset to a new value. This is what I represent here. Well, this is a figure adapted from the book of Lisikiewicz. And this reset value is below the resting value. One can take this peak and reset values to be realistic and to have dimensions, and typically that's the way the people models this QIF model. When eta is positive, then this parabola doesn't, well, this function doesn't have zeros, and then the neuron becomes an oscillator, so its membrane voltage is going to this peak value constantly, and then it's reset again and again and again, and it becomes an oscillator. Okay, there is a correspondence between the quadratic intercamphire model and the so-called theta neuron model. If these peak and reset values are taken to be at infinity, so the QIF model reaches infinity in finite time, then the QIF can be formally transformed into the so-called theta neuron model using this transformation of variables that was proposed by Ermentrout and Coppell. This is a so-called phase model, because now the cell is not described by a membrane potential but by a phase. Okay, and this transformation of variables maps the real line on this circle. Okay. Now I want to go to the collective dynamics of networks of these neurons, and I want to focus on a recent theory that has been developed originally by Ott and Antonsen in their celebrated paper of 2008, and this theory allows to obtain an exact low-dimensional description of a network of Kuramoto oscillators. Okay, these oscillators are coupled via sinusoidal coupling of the phase differences between pairs of oscillators. The theory allows to, as I mentioned, allows to obtain mean field description in terms of a mean field parameter that is the Kuramoto order parameter. Later, after the original paper of Ott and Antonsen, it has been shown that the Ott-Antonsen theory also holds for other phase models that are relevant for neuroscience. For instance, it holds for for so-called Winfrey oscillators, which are pulse coupled. They are not coupled now with sinusoidal pairwise phase differences, but they are coupled with pulses, and this is highly relevant when one wants to model chemical transmission, and the model also has PRCs. But what is more relevant for us now is that this theory also holds for networks of pulse-coupled theta neurons. Okay, this was shown by Luke, Barreto, and So in 2013, and this model has been investigated and extended and refined by Carlo Lang, by Steve Coombs, and by many others. But in computational neuroscience, it is often so mean field models are often formulated in terms of they are not formulated in terms of a mean field quantity that is the Kuramoto parameter, but they are formulated in terms of activity or of firing rates. And these models are the so-called firing rate models, or Wilson column, or neural mass models, or neural field models. they have different names. These models are generally heuristic, or they are derived under approximations, but they are never exact. And then one may wonder whether these mean field descriptions that are exact could be reformulated or written in terms of or related to this class of models. So starting with the QIF model, it is indeed possible to derive an exact firing rate equation for a network of QIF neurons. And actually, this description can be linked to the description in terms of the Kuramoto order parameter via a conformal map. So this is the unit disk where the Kuramoto order parameter evolves. So, and this is a new, say, complex number which has one component is the imaginary axis here represents the mean voltage, and the real axis here represents the firing rate. So this W is composed of firing rates and mean voltages. And then this conformal map links these two descriptions. In particular, when this Z has modulus 1, say when all the theta neurons have exactly or are exactly at the same state, then we evolve in this circle here, and then this transformation reduces to the transformation I explained earlier, and that is the transformation that links QIF and theta neurons. So this can be seen as a generalization of this transformation for this mean field order parameter, for these order parameters, the Kuramoto order parameter and this order parameter based on firing rates and then potentials. And now let me explain briefly how to derive these mean field, these firing rate models. So now imagine that we have a population composed of an infinite amount of QIF neurons, and they all have the same eta. Okay, and suppose that this eta is now positive, so that this parabola now, so that this function now doesn't have any zero. So neurons are constantly firing, but one can, but it turns out that this density can be stationary. So even though these neurons are constantly firing, one can imagine that there exists a density that is peaked around the minimum of this parabola, and it has a certain width that we will call x. And this density, in order for this density to be stationary, it should be inversely proportional to the speed of the neurons, which is given by v squared. So it should be inversely proportional to v squared. And then x and y is the center of this distribution, and x is the width of this distribution. And this is a Lorentzian distribution. In general, these x and y's are going to depend on eta, okay? And then we will have many different etas. In our theory, we need to adopt the thermodynamic limit, but we also need to adopt the limit of v going to infinity. So we are not resetting and thresholding the cells at finite values, but at infinity. So this density is defined from minus infinity to plus infinity. So the voltage is going from minus infinity to plus infinity. But still, in simulations, we take these as finite values. And therefore, one needs to think of this theory as asymptotically valid in the limit when this reset and threshold values go to infinity, okay? And in the limit of infinitely many cells. Okay, now if one considers these ansatz or this density, it is easy to compute the firing rate by multiplying so v dot by the density and performing the limit Vp going to infinity. P is the peak of the spikes, and then it's very easy to compute this limit, and it gives x. So x divided by this, but essentially the firing rate for each value of eta is given by the width of this distribution. Whereas the mean membrane voltage can be calculated integrating from minus Vr to plus B to Vp, the density times V. So this is the first moment. That would be, this integral would give the first moment of this distribution if this was minus Vr to Vr, okay? let me now explain what is this ABR here, but for now on, so you see that this integral corresponds to the first moment of the distribution, but now one has to, but since this distribution is Lorentzian, it has heavy tails, it cannot, this distribution doesn't have finite moments, so one needs to adopt this limit. So this is the principal value. This is the Cauchy principal value. So the mean voltage is given by this integral. And now notice that Vp is written as a constant. This constant, I wrote this as a constant. This is a real positive number, okay, that multiplies Vr. Thus far, only the case A equal 1 has been considered. So in the theory that I will now develop, only the case from minus Vr to Vp has been taken into account, but one can also perform this integral for these arbitrary limits. Okay, so taking the peak and the receipt values at different places, and this will account for the effect of asymmetric resetting of the cells. So let me show you how the spikes look like. So this is a simulation of the QIF model, and now I cut the spikes at 100 and I reset them at minus 100. In this case, this asymmetry parameter, which is the ratio between Vp and Vr, is 1. But these spikes, which look a bit more, say, realistic, have A equal 4. So this is 4 times larger than this, okay, in models. This is what I'm now trying to describe. So the mean voltage now is, as I said, is this integral, but this integral can be written in 2 parts. So it can be separated in two parts. Okay, it can be separated in this limit, the limit of this integral. This will give capital Y. So this is the center of this distribution. This gives this number here. If one performs this integral in a say symmetric, with symmetric limits, one will get this Y with this, but then we have this extra factor that here that can be evaluated. And then we get that the mean voltage consists of this Y plus an extra term that depends on X, and X is the firing rate. So the mean voltage now is not simply the mean of the distribution, but it also depends on the firing rate. And this logarithm, this natural logarithm of A, controls the contribution of this term. Okay, if A equals 1, the spikes are symmetric, and this term is not here, and then the mean voltage corresponds to the mean, to the center of this Lorentzian distribution. But if not, then we have an additional term. Now, let me very briefly explain how to obtain the firing rate equations. We compute the mean firing rate by integrating these x's for all etas. So this is a distribution of the inputs that the neurons receive. So this is a source of quenched noise in our system. And then we will have also the mean membrane potential, that is this integral over all v's. And since v is composed of y and x, this integral corresponds to these two integrals here. And now the procedure to obtain the firing rate model is standard. So we write the continuity equation, we plug the Lorentzian ansatz, which corresponds to the Otto-Antonsen ansatz, but in a different space. So the correspondence between the Otto-Antonsen and this Lorentzian ansatz is this conformal map that I was talking about. And then we consider a distribution here, which is also Lorentzian. And it's centered at some eta bar, and it has a width, certain width delta. Okay, this delta will measure the amount of heterogeneity in our population, and this is the mean received. If this is I choose this distribution to be Lorentzian because then these integrals can be solved by applying the Cauchy's Cauchy theorem, and it turns out that only the only relevant value of eta is the value of eta at the poles of this distribution. Okay, and that's why we get a strong dimensionality reduction. And the model that we find is this one, where here we have the mean firing rate, and here we have the mean membrane potential. And then you see that the asymmetry parameter enters in 3 different places. So it looks like very non-trivial, no? The effect that this asymmetry has on the dynamics, on the collective dynamics of these models. But if one, so you see that it affects the membrane. So well, it enters here, and it also shifts the distribution of currents, and it also enters into that part of the equation. But if one defines this, if one uses this auxiliary variable that I will call VA, which is not the voltage, is an auxiliary variable that contains V and R, and it reduces to V when A is 1, then the model turns out to be this model that do not contain A's anymore. Okay, this is exactly the model when there is symmetric resetting, but substituting VA by V. And this says that there is no qualitative change in the dynamics of the model if one introduces this asymmetry in the coupling, in the firing of the cells. Okay, so this is not so good, but well, or perhaps yes, but so this result is not offering anything new, so there are no qualitative differences between the mean field dynamics. But in this model, I didn't introduce synapses, so now I will model chemical synapses and electrical synapses. So I will couple the cells. Okay, chemical synapses, I will model them as current-based synapses. So you know that current chemical synapses are connect virtually all neurons. They are directional. They can be either excitatory or inhibitory. They have relevant time delays that relevant for the dynamics they may have, but here I won't go into that. And what is very important is that they are all or none. So when the cell fires, then these synapses are activated. In contrast with electrical synapses, okay? Electrical synapses are common among inhibitory neurons only. They generally are symmetric, they are instantaneous, and they are always on, okay? Because they connect, they are gaps between they are gap junctions between the membranes of different cells, and therefore so the two cells are constantly receiving currents from the other side, okay? Especially when there are spikes. The firing rate equations with chemical and electrical coupling have been already derived, first by Carlo Lang and then by Pietras et al. In the case of symmetric resetting. And so this is the microscopic model. This is an ensemble of QIF neurons. Here I put the chemical coupling, which is mediated via the firing rate, the mean firing rate. And this is the mean, and this is the electrical coupling, which is mediated via the mean membrane voltage. And then the corresponding firing rate equations are these ones, where the chemical coupling appears here in the mean voltage, and it shifts actually the distribution of voltages. And surprisingly, the effect of electrical coupling, it doesn't enter here. It doesn't have a diffusion, so it doesn't have this form as a diffusion here, but it enters in the R dot equation, and it tends to reduce R. And this means that it tends to reduce the distribution of voltages, favoring the appearance of synchrony. So it tends to equalize the membrane voltages of all cells. So this is a nice result, but this model doesn't explain a number of results that have been observed in computational models. In particular, this is a spikelet of a QIF neuron. So this is the membrane potential of a postsynaptic neuron, and how it responds to a spike of a presynaptic neuron due to the presence of an electrical synapse for different values of this asymmetry parameter. And you see that when A is 1, when the spikes are symmetric, so this so the spikelet has a clear say positive component, but also a long-lasting negative component. But this is like strongly modified when we change A, and therefore we expect that A has a large impact in networks with electrical synapses, and this is not surprising. This is already known, and it has been investigated in many computational studies. And these studies, computational theoretical studies, say that synchrony is crucially affected by the shape of the spikes. And moreover, that the effect of electrical and inhibitory synapses may sum linearly. And we don't see that in that model, right? So we see that electrical and chemical synapses are acting in different places in the equation. So now we derived the corresponding firing rate equations that include this asymmetry in the resetting, and we find the model that we had earlier, but now we have this extra term in this auxiliary variable. Okay, so this is now not the mean membrane voltage, is this auxiliary variable, but you see that electrical synapses now enter, or the effect of electrical synapses, it also enters in this part of the equation, and it sums, or it adds to chemical coupling. That's why I say that electrical synapses introduce this sort of a virtual chemical coupling due to the presence of asymmetry in the resetting. And this explains the results, a number of results, but especially this one of Felty et al., that electrical coupling may compete or cooperate linearly with inhibition. This is the phase diagram that one can obtain analytically from these equations. So these lines, these red lines here are Hopf bifurcations, and these are SNCC bifurcations. These boundaries separate the region of synchrony. So this is synchrony from the region here where there is no synchrony. And this is the mean input that the neurons receive, and this is the strength of electrical coupling. So this is for A smaller than 1, so the spikes are more inhibitory. This is the symmetric case that has been already analyzed, and this is the spikes that have a threshold, a peak that is larger than the reset. And you see that these spikes have a much broader region of synchrony. And this explains the results again of Felty et al., that now of a different paper, that electrical synapses may favor or impede synchrony depending on the resetting asymmetry. And finally, let me show you results of simulations. I took here, I consider eta to be 1 and g to be 2.5. I'm here in this cross here, and I'm changing the value of a. Okay, so in the first row, I show you a equal 1/4, and the peak value now is 100. And you see that we don't have oscillations here, we don't have synchrony because we are outside this area. Okay, and in the black curve corresponds to simulations of the QIF network, and the red curve corresponds to the firing rate equations. Then as A is increased, we enter into the region of oscillations, and the amplitude of these oscillations is increasing. And then you see clearly how the model deviates from how the network simulations deviate from the firing rate equations. And this deviation is essentially, well, there is a clear difference in the period of these oscillations, because now we are resetting the cells earlier. Okay, they don't reach infinity; they reach 100, and then we reset them at minus something. Okay, but then we see how these simulations or the agreement improves as we increase the peak value at which we reset the cells. Okay, and that's the last slide, and I want to thank you for your attention. Thank you very much.
Thank you very much, Ernest, for your talk. There was a long time ago a question, I'm sorry, but we decided to answer them at the end of the talks. So there's a question by Tom Burns: what happens to the density of membrane potentials if the threshold or reset potentials are variable or even probabilistic, especially over time. So if you consider adaptation, for example.
Can you repeat the question? What
you can also read it, but I can repeat it.
No, tell me again, sorry.
So what happens to the density of membrane potentials?
Yes.
If the threshold or reset potentials are variable over time or probabilistic. So if you consider adaptation, for example.
The answer is that I don't know. I didn't analyze this case. Well, maybe this case could be say simulated, introducing an external current that is oscillating, perhaps, and then we are okay, approaching the threshold or going away from the threshold periodically. And then what we have seen, for instance, is that if you introduce a periodic current, you can find, for instance, collective chaos in the model with two equations. I mean, and yeah, for instance, that I don't know. But adaptation, I didn't. Well, I think there is a group that investigated this model with spike frequency adaptation, but now I don't remember what happens.
There is a second remark and question by Marc de Camps. So I thank you for your very nice talk.
Oh, thank you.
This is not a question. So did I understand correctly that you make Lorentzian assumption throughout?
Twice.
Twice.
Yeah. Well, yeah, you use this Lorentzian all the time. Yeah. Right. We assume that the density is Lorentzian, and this assumption is because the density must be inversely proportional to the speed of the neurons for the density to be stationary. But then there is another say trick, something different, which is a trick actually, that is that one needs to solve this equation in order this integral, sorry, in order for the continuity equation to become low dimensional. So you see that this x here, which is the firing rate for each eta, they depend on all etas, and therefore, in principle, these continuity equations are infinite dimensional, so they contain all etas. So we have an infinite amount of coupled continuity equations each for each eta. So one for each eta, and therefore one needs to. So this trick was proposed by Ott and Antonsen, and if you select, and the trick is to use the Cauchy theorem, and since the Lorentzian distribution has a single pole, then well, it has two single poles, but one can solve this integral by complex integration around one of these poles, and then one reduces the dimensionality to two equations. Okay, that's the idea.
So Mark, your question is much longer. I didn't read all of it. Are you happy with this answer and would okay? Because I think that we all also would like to have a short coffee break.
Okay.
So
okay.
I propose to stop the session here.
Cool.
Okay,
Yes.
I can take it up later.
Yeah, so there will be a coffee break now, a virtual coffee break.
Yeah,
so
we are
we
missing.
will, everybody can take some coffee at home or wherever.
Thank you.
So we will reconvene at 17:30. So there is, in this channel, there will be a session on neural coding. And in channel 1, there will be a session on cellular and subcellular dynamics. So you can also use the coffee break to also enter the Slack channel where you can have discussions about the talks that you have heard and or other stuff. Okay, so with this, I would like to close the session and thank all the speakers again. So it was great. Thank you.
Thank you.
Thank you. Thank you.
Bye-bye, Ernest, and all the speakers and all the others.
Yes.